Okay, let's continue now. Part 2. In part 2, we're going to consider Joseph's problem. So let's consider this problem number 3, which says prove that, okay, j of 2 to the power of m plus l equal to 2l plus 1. Now, if you recognize this, this is closed form for the Joseph's problem, right? So we have the recursive formula and we have the closed formula as well. So we need to prove it. We're going to use mathematical induction. I'm going to prove it only for even, and for odd values, you're going to do it yourself as a practice problem. So I strongly advise you to do that. So let's start with this one. First case is the base case, right? So in the base case, we're going to consider that m equal to 0. So if m equal to 0, right? So according to the condition, it could be 0, right? Then what do we have? Well, we have to look for this condition, right? So my L must be strictly less than 2 to the power of m. So if m equal to 0, right, means that 2 to the power of 0 is 1, which means that my L must be strictly less than 1, right? So L must be less than 1, right? And what is the only value for L? If L must be less than 1, but greater or equal than 0. So the only value for L remains to be 0, right? So L also must be equal to 0. So in this case, we have m equal to 0, L equal to 0. Then I'm going to use now check this formula, right? So j of 2 to the power of 0 plus 0, right, will give us 2 times 0 plus 1, which is equal to 1, and which is true by inspection. Okay? By inspection, because we can verify it checking manually, right? Okay, next case is, now we're going to assume that when m is strictly greater than 0, that if m strictly greater than 0, and remember that we are doing this only for even values, right? So not even values of m, but even values of j, right? So if m strictly greater than 0, and we're considering even values, we're going to say that this number, 2 to the power of m plus l, is even. Okay? Or we can write it as equal to 2n. And n, in this case, some integer. Okay, so if m is greater than 0 and this value, this number is even, we're going to assume that the formula will give us correct answer, right? Or we're going to assume that it is true. So I'm going to write over here that j of 2 to the power of m plus l equal j of 2n should give us 2 to the power of l plus 1. We're going to assume that it is true. Okay? So in the third step, now we're going to prove that for the very next even number, right, the formula also gives us correct answer. So that is, if my current number is 2n, the next even number is going to be 2n plus 2. So I'm going to write it over here, that proof for 2m plus 2 equal 2 to the power of m plus L, that it is also true, right? So remember, when we do math induction, in the third step, we use the assumption that we made in the second step. Okay, now I'm going to start with this one, j of 2n plus 2, right, which is the very next even number. Now, if I'm going to move 2 outside of the brackets, right, but it's still inside of j, right, I will get 2 times m plus 1. Okay, and over here I'm going to use recursive formula for Joseph's number. Remember, recursive formula for Joseph's number is given by this formula, right? For even values, j of 2n is equal to 2 times j of n minus 1. Okay, we're going to use this, and by this we're going to get 2 times j of m plus 1 minus 1. Now, for the next step, for j of m plus 1, we're going to substitute into m plus 1 this value. So over here, if you look, we have 2m plus 2. If I take 2 outside of the brackets, right, I will have m plus 1 times 2, that is, and if I divide by 2 both sides, I will get over here 2 to the power of m minus 1 plus L over 2. Okay? So for this very next step, I will get this. 2 times j of 2 to the power of m minus 1 plus L over 2 minus 1. And over here, we're going to use our assumption that we made in the second step, right? That this formula actually gives us this answer, right? So if you have j of 2 to the power of m plus L, well, the result of j, okay, of that number is equal to 2 times L plus 1. So since we assume that it is true, we can use it in our case over here. So I still have 2 to the power of m minus 1, right, which corresponds to 2 to the power of m, and plus some integer value, right? Over here I have some integer value L over 2, okay? So by this logic, I will have 2 times, again 2 times, instead of L, I will have L over 2, and plus 1, and outside I have minus 1. Okay, so this 2 and 2 go away, and I have 2 outside, right? So if I open up the brackets, what do I have? I will have 2 times L plus 2 minus 1. So I'm going to write it over here. So 2 times L plus 2 minus 1, and which is equal to 2L plus 1. So this is it. This is proven. In the same logic, you can do it for odd values, okay, of j. So that is, if this value 2 to the power of m plus L is odd, you follow the same steps, use the same logic, and you're going to get to the same conclusion. Okay, let's move to the next problem. Now, next problem is more general, right? This is about logical conclusions, and how we can prove or disprove it. So in this case, we have the following statement. The statement is like this. Pn indicates this, right? That the product of these values, x1, x2, and so on until xn, is less or equal than the sum of these values, x1 plus x2, and so on until xn, divided by n. What does it mean? It means that this is the average value of x, right? Raised to the power of n. So this is the statement. And it says that this is true for all x's that are positive. So this is the statement. The problem is to prove that if this statement is true, Pn, then this statement must be also true. That is Pn minus 1. P of n minus 1 for every n strictly greater than 1. By setting xn equal to the sum of x1, x2 until xn minus 1 divided by x minus 1. So let's approach this problem. So Pn implies Pn minus 1 basically means that if Pn is true, then P of n minus 1 must also be true. So this is what we need to prove. Now let's start with our assumption or supposition, right? We're starting with the condition, right? The condition is that Pn first must be true. So we're going to assume, okay, suppose that Pn is true. Which means that the product of x1, x2 until xn is less or equal than this expression. Okay, the sum of x divided by n raised to the power of n. So I'm going to write it over here. x1 times until xn less or equal than the sum of x1 xn until xn divided by n raised to the power of n. Okay, so what we need to start with is by setting xn equal to be this, because this is what the problem says, right? So if I'm setting xn to be equal to this, right, then in this expression and in this expression I have to substitute xn with this expression, right, with this sum of x's until xn minus 1 divided by n minus 1 over here and over here. Now the question is, what do I have before xn? Before xn I have xn minus 1, right, in this case and in this case as well. So I'm going to spell it out separately over here. So I'm going to write it x1 product until xn minus 1 and multiplied by this expression, right, which is basically a substitution for instead of xn. Now, which is less or equal than this expression. So x1, we also have xn minus 1 over here, and the sum of this. Okay, next what do? We can bring this, right, the upper side to a common denominator, right? And we will see that actually we have the same expression, right? So you have the same expression over here, x1 plus x2 until xn minus 1, and over here we have the same expression. So I'm going to write that this is equal, this expression is equal, right, to this one. So I have n over here, n minus 1 And over here I will have n minus 1 multiplied, if I bring it to common denominator, multiplied by x1, the sum of x1, x2 until xn minus 1, plus this sum as well, which is x1 until xn minus 1. And I have the power of n. Now for the next step is this n minus 1, right, goes down, and we see that n minus 1 times the sum of x1 until xn minus 1, and over here we have the same expression, right, x1 plus x2 until xn minus 1. So if I take the sum, basically this is this expression multiplied by n, right? So I will write it over here. Now this is equal, this is continuation. This expression n times n minus 1, and over here I will have n times x1 plus until x minus 1 raised to the power of n. Now this n cancel out, and I have finally this expression n minus 1 over here, and I have x1 plus until xn minus 1 raised to the power of n. For the next step, what we can do is we can actually see that this expression, right, is the same as this expression, the last one, right? But what we need to prove is that p of n minus 1 must also be true if pn is true, which means that, okay, this expression must go. So I shouldn't have this expression over here. So to do that, we can slightly transform this expression, right? We can write or rewrite this one as n over here, n minus 1 so I have basically this expression multiplied by itself n times. So if I take out one term outside, or write it separately, then I can write it like this, right? So this expression raised to the power of n minus 1 multiplied by the same expression. Okay, so if I again bring it back, then I will have this, because they are the same, and when you multiply the same, right, the powers will add up. So great. For the next step, basically I have this expression on my right side and this expression on my left side. So I'm gonna erase this part and write it over here. So x1 times until xn minus 1 multiplied by this less or equal than x1 plus until xn minus 1 divided by n minus 1 raised to the power of n minus 1 times the same expression. Okay, now we see that this expression and this expression are the same. And since we know that x1, x2, and xn all are positive and they are arbitrary, so I'm going to write over here that my xn, okay, x1, x2, xn are, okay, arbitrary. And also I know that this expression is positive, right? Since my x's are positive, okay? And we are proving this, right? This expression for when n is strictly greater than 1. So over here, n is strictly greater than 1, right? Implies Pn minus 1 for all n greater or equal than 1. That means that this expression is positive and x1, x2, xn are arbitrary. We can safely cancel out this expression on both sides. And therefore, which will give us what we needed. So this is it. If this is your Pn statement, then this is our Pn minus 1 statement, right? And we proved that. We suppose that Pn is true, and by using manipulations, we came to the conclusion that this expression is also true, which is P of n minus 1.